Another family of visualizations is aimed at figuring out if there's a relationship, in particular between two numeric variables. I know the terminology is a little confusing because it's like, well, aren't we looking for relationships everywhere? Like, isn't that the point? Yeah, sort of. But here we're talking about specifically things like trend lines. So if you remember, we can do things like just a normal linear trend line. Here we're trying to define a metric of error. Maybe it's minimizing squared error or something like this. You can define any error metric you want. And then there is a line, or maybe multiple, oftentimes unique, but depending on which metric you use, perhaps not, a line that fits the data cloud best. Like it's a line of best fit under some metric. And I know that's a little vague, but at this point in our careers, we have to kind of open our sights up a little bit. Like it's a much bigger thing out there than just the ordinary least squares line, like kind of thing you're always presented in class. Regardless, here's a relationship. We have a relationship in which as birth rate goes up, average life expectancy in women goes down. There is a lot of reasons this could happen. And in particular, there's a causation reason. Giving birth is a difficult and dangerous procedure, or process rather, especially in parts of the world that have developing healthcare systems or bad prenatal care or bad postnatal care for mothers and children. And so actually having more children may actually may kill women and drive life expectancy down. It may also be the case that these things are just correlated. They're not actually causally related as much as we might think, meaning that there might be another factor that's driving both of these variables, like wealth, for instance. Regardless, we have to be very careful, and we'll talk about this more in a moment, about what exactly we're claiming here, because if we say if average birth rate goes up by 0.01, then on average life expectancy decreases by 10 years, we have to be careful to clearly articulate to non-technical stakeholders what that actually means. So more on that in a moment. Also point out that it does not need to be the case that the line of best fit is a linear function. For instance, here I'm looking at GDP over time, and it's a little hard to tell, but this line is definitely curved. So this is an exponential best fit rather than a linear best fit. And you can define, again, like any best fit line you want under whatever error metric you want. And so this kind of wider world makes it a little bit more difficult to communicate with the folks we need to. So getting to that, relationships are just relationships. You are not saying that one of these things causes the other. And it's really, really important to keep driving this home, because even the way we teach students to phrase the results of linear regression, for instance, as x increases by 1 unit, on average y increases by beta, all else equal, that it does not explicitly say anything about causation, but people put that story in themselves. They say if x increases by 1 unit, it's causing y to increase by beta units. And that is not true. It's just saying that they are related in the following way on average. We have to keep driving this point home. And I hate to put so much burden on us, but like as the presenters, as the people that are displaying these results, the responsibility really is on our shoulders to make sure that there is as little danger in misinterpreting our results as possible. So we're the ones that have to continually remind the audience, like, wait, this is not what we mean. It's not causation. It's just correlation. That's all I'm claiming right now. Similarly, we need to be really careful with things like p-values and r-squared and the coefficients themselves, and exponential growth rates, and all of the other technical terms that kind of fall out of these mathematical procedures that we're talking about, things like fits and all of this. And the reason being that people don't understand p-values. You know what I mean? They don't really know what that means. Even r-squared, they know the bigger the better, but they don't really know. And so we have to be really, really careful. And so I guess my bigger point with all of this stuff is, whether you're thinking about a trend line or including a p-value or including an r-squared or including the exponential growth rate, regardless of which of these technical pieces you bring into a visualization, regardless of which ones you bring in, you need to have a good reason for bringing them in, and you need to clearly explain somehow what the heck they mean. Because the purpose of a visualization is to take a complicated situation and display it in a visual format that makes it easy for everyone to engage with. The more of these technical pieces that we bring in, the more difficult it becomes to engage with at least the whole story. Now, it might be the case that, like, for instance, you have a visualization that shows the trend line, and that's it. And then in a write-up, you might say, here's, and then blah, blah, here's the basic situation. For a more, for a more technical audience, see the footnote, and then you explain all the details down there, or it's in an appendix or something like this. But there are strategies we can use, but my big thing is just be careful. Keep your audience in mind when you're displaying these things, because not everybody will be able to follow you into those kind of more mathematical realms. But again, we'll get to practice all of this as time goes on.